Hello everyone, welcome back to Premium Course BAC. Today we will discuss about design verification, the software with design menu. I have my premium Excel set. You can contact me by Gmail, luyimba168@gmail.com. This design column, design steel beam by using Excel set. Now come back to Tekla Structural Designer. We continue from the previous tutorial how you can assign and edit restraints by using 3 different methods. Now click on the right beam, the left beam, edit, and edit the property. I want to change the restraint and change it to 1. So this beam there is no restraint at the top and at the bottom flank. We design only change it to 1. Now let's change it to 1. Enter. Okay. So this beam only has the support at the start point and at the end point. You see this distributed this load and line load. The impulse load, the line load is 4 kilonewton meter, and this load is 2.0 kilonewton meter. And after we change the restraint, the lateral restraint to 1.1. So this main beam, no restraint to prevent lateral torsional buckling occur on the main beam. Okay, now let's start run analysis and design. Use the option to run analysis design and check the beam. Take mouse over the beam. The design ratio is 1.672. Okay, now click on the moment and change it to the envelope. The maximum moment is 40.5. 40.5. Input it in my Excel set. Change the section. You can change to section IPE 400. The Excel set will be automatically update the section property and other parameter. Now let me keep it in 200. And input the SY, the G strength of the beam is 235 megapascal, and the apply moment is 40.50. Yes, 40.50 is correct. Okay. And the beam length is 6,000 millimeter, and the K, you the coefficient 1, keep it 1. Now let me check and verify with the Tekla Structural Designer. Show me the result, and the result is 1.672. In my Excel sheet it 1.67. Yes, we use the methods for the I and H shape profile or equivalent bed dissection, close 6.3.2.3. In a general method, you use a general approach, close 6.3.2.2. This method has a higher result than the lateral torsional buckling verification by using the equivalent bed dissection. This one is the most economic method for the profile I and H section only. Okay, we can apply it for the I and H section only. For other shape, you use the general approach for design. Now let's check for more detail about other conditions. Okay, click on the main beam, right click, check the member, static, and classification is class 1. Okay, check. The classification is class 1 is correct. And the shear is 27.0. You can input shear here. 27.0. Now let me input it the same. Shear, yes, and design capacity is 189.9. Yeah, 189.9 is the same. And the buckling and the moment, yeah, the moment measure moment is 40.5 kilonewton meter, and the design capacity is 51.9. Yeah, if 51.9 is the same here. And buckling, lateral torsional buckling is 24.2. Yeah, 24.2. Scroll down, and yeah, we keep its signature is correct, and the K factor 1 is correct. Now let's check here. 24.2. Yes, this one. BOD is 24.3. Okay, let's check it. Yeah, 0.3. It's similar in Tekla Structural Designer is 24.2, and the design value they apply moment is 40.5. Yeah, in my static is 24.3, and the design ratio is 1.67. 67. Okay, come back. Now let me check and change the lateral torsional restraint on this beam. Come back to restraint. I change it to 0.5. 0.5. In the case, we can, but they are similar with this picture. The main beam has a sub beam, has two sub beam at the middle of the main beam to restrain to prevent lateral torsional buckling occur on the main beam at the middle. Yeah, like the picture. So we use the option to input and correct the factor directly without the sub beam. Okay, now let's design and design check. The ratio is 1.074. Now let me change only the K. Only the K. 0.5. 0.5. Okay, now the result is 1.09. Yeah, 1.07. It's similar. You can check the static. Right click, check static. Yes, 37.7. For the buckling, this 37.3. Okay, and for the moment, 51.9. Yes, the same, 51.9. Okay, now you can continue to change the restraint. Edit, and lateral restraint I change it to 0.3333. 0.33333. 0.33333. Enter and copy, and come back to run analysis design again. The result is 1.004. Yeah. Now let me change the K to 0.33333. 0.33333. So the result here in my it says is 0.94 in this Tekla Structural Designer. The result, yes, 0.9, yes, 0.9. If you compare only for the lateral torsional buckling, so it's okay. The deflection is 1.004, okay, 0.9, okay, it's similar. This is the way you can design and check verification with the set. I will check more detail on the parameter and how it's important on each parameter. Now let me come back and I change it to the 1 strength. Now let me change it in the 1, okay, and design it again. Right click, check static, okay, and click on the expand all to expand and check everything. Now let me change it to 1, okay. Now you can check everything. Yeah, the class is 1, class 1 is correct. And VCYOD 189.95. Yeah, it's the same. And for the measure moment, yeah, 51.9. It's the same. And the length LLTB is 6.00 meter. So now we input this length and keep the vector k is equal to 1 is correct. And the table C1 is equal to 113. Yeah. Now let's check the C1. Yes, it's correct. It's 1.32. In Tekla Structural Designer, only 113. And KLB is equal to 1 C1. CO 25.8. Yeah, 25.9. And design buckling restraint 24.2. Design buckling restraint MBOD 24.2. MBOD 24.3. Yes, it's similar. So now I will tell you what important how to check and verify all the member. The first one, you should understand about the load condition. We apply the load condition. There are different destabilizing and stabilizing. Destabilizing, what does it mean? The load applied on the member and the section can twist over its own axis without stabilizing, without the sub-beam to prevent lateral torsional buckling or to prevent rotate of its own axis of the main beam. This is how we can select the destabilizing and stabilizing. This load condition apply on the main beam, apply on the frame is very important. You should understand about stabilizing and destabilizing. And other one is the type of load applied at the C center, or apply on the top and apply on the bottom plane of the member. It also impact on the design strength of the member, design capacity of the member, because almost software will be applied at the C center. Actually, the load never really applied at the C center. It's applied on the top and on the bottom of the plane only. Yes, when you apply on the top, the design capacity is more higher when you apply at the C center. Okay, now let me check at the C center. Yeah, it only 1.67. When you apply at the top, it's 1.89. So the result is very important when you apply on the load. Yeah, 1.89. This is how you can apply the load. Should understand the real condition or the apply load on the member. Yeah, in all the software, almost software use the option in the default. Yeah, it apply at the C center. In the real structure, this load apply at the top of the center, or the top of the beam or the top plane. And other one condition is the condition of the beam, the restraint. Yeah, the restraint of the beam. You design it as a fixed support or pin support. In the condition, we design a simple supported beam. Yeah, when you design in a simple supported beam and you change it to the fixed support, the result also different. It is the earn condition or boundary condition or the support is very important and affect on the result of the member. Okay, and other one is the load condition. Load applied distributed or apply at the point load at the center or any portion of the beam. It affects on the factor of the C1, C2 and C3. Yeah, C1, C2 and C3. C1, C2 and C3, when you apply load at the top, so the eccentricity from the top to the center, C center, it must to be taken into account for design. So C1, C2 and C3, when you apply it at the C center, we do not include the C3 in yeah, you see here the ZG is the distance from the applying position to the C center is 0, and when you change it to the top, now the ZG is 100. This is the way of the applying position of the load, and the load condition, distributed load and point load affect on the different condition of the C1, C2 and C3. So the result of MCO also different. And this is a very important. When you design beam, you should understand the load, the beam condition, destabilizing or stabilizing, and the load applied at the top of the plane. Yeah, top of the plane, the C center, or at the bottom of the plane, and the earth restraint of the beam at the ends and at the bottom, at the start point. What is the restraint of the beam, fixed or pin support? Yeah, and the apply load, distributed load, fully apply on the beam, or point load apply out on the center of the beam, or apply at any point of the beam. So the value of the C1, C2, C3 will be changed on this input parameter. And the last result, the method you use to design for the lateral torsional buckling. For general approach, or use equivalent dissection. Equivalent dissection you can apply and use it for the member has shape I and H section only. For other member, you can use general approach. General approach used for the overall member, include I, H, and other member, but the result is different from the method for I and H member, or equivalent valid section. The result is acceptable and very economic for designer to select the method only for the I and H section. I use this method for design for I and H section only. For the other method, we use general approach for design other shape or section. I hope you enjoy the tutorial.